Okay folks, it's Mr. Willis here, and today we're going to work on graphing a little bit because I graded your lab papers and your graphing wasn't very good. And so what we're going to do here is I'm going to show you how I would do this problem. This is the one that is on the back of y'all's quiz, 43.1 and 43.2, that the sub should have just handed back. So if you would turn over that quiz to the back, and we're going to take a look at this, and this is what it looks like, and I want you to see what you did, see how I do this problem, and see if you can figure out where you missed your points. And then what I'm going to do in the last 20 minutes of this class, the sub is going to give you another graph that's similar but different, and you're going to have to do that one and see if you can get a better grade than you did this first time around. A couple of y'all did fine, but many of y'all did poorly. So you want to pay attention to how I do this, and then try and do it better today. So pay good attention here, and you'll figure some things out about graphing, hopefully. Okay, so here we go. And you can read along if you can't see it on the overhead well enough, on the board, on the screen well enough. An experiment was conducted to measure the reaction rate of human salivary amylase. It's an enzyme, and that's the enzyme that breaks down sugars in your mouth, believe it or not. So they said 10 milliliters of a concentrated starch solution and 1 milliliter of alpha amylase were placed in a test tube. So the amylase is going to break down the starch. Test tube was inverted several times to mix the solution and incubated at 25 Celsius. 25 Celsius is a kind of about room temperature, maybe a little bit warmer than room temperature. If you're wondering, your body temperature is 37 Celsius, I think. That's a good number to know. Anyway, the amount of product present was measured every 10 minutes for an hour, and the results are given in the table. So here's the time they've taken the readings, and here are the results. This is the maltose concentration. Maltose is our product. Starch is our reactant. So starch is reacting and forming maltose. All right? So this is an enzymatic reaction. An enzyme is tearing apart the starch and making it into maltose. Yay! Maltose is a disaccharide, a simpler sugar. Starch, remember, is a polysaccharide. So, graph the data on the axes provided and calculate the rate of reaction for the time period 0 to 30 minutes. So I'm going to graph this, and when I look at this, I see that the time goes all the way up to 60 minutes, and the maltose concentration goes all the way up to 11.5 micromoles. So I'm going to construct my graph keeping that in mind. I'm going to put time on the bottom, and you have to make sure you put it in minutes. And the reason why I put time on the bottom is that's the independent variable. What you control as the experimenter goes on the bottom, and I'm controlling the time. And I'm going to make the time go all the way to 60 minutes. I'm going to put 0, I'm going to put 10, 20, 30, 40, 50, 60 minutes, leaving 2 boxes on each. You could go put a hash marks here so you know what is the particular reading. I could have probably gone 3 boxes and then 10, and 3 boxes and then 20, and still had enough room on the graph. But that's okay, this will work. I'm using at least half my graph, which is kind of the idea. You want to use at least half the graph. You don't want to go 10, 20, 30, 40, 50, 60 and have only used a third of the graph. You want to use at least half of each axis. And so on this side, I'm going to go, I've counted there's 22 boxes, so I'm just going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's my maltose concentration in micromoles. And by the way, if you do not put these units, you get counted off. They give you a point for putting the correct axes here with the units. So for orienting the axes correctly, if you put time over here and maltose concentration here, you got it wrong. It's always a good just rule of thumb that whatever you're measuring goes on the y-axis. So we're measuring from the results of the experiment give us the maltose concentration. That's on the y-axis. We set up how long we're going to run it. We set up the time, how long we're running it, so that goes on the x-axis. What you set up is on the bottom, and what you measure is on the side. It'd be a good idea to put a title on my graph. I'm going to put maltose concentration in micromoles versus time in minutes. And they did not give you a point for putting this, but you never know. Maybe they will, so you go ahead and put it. So sometimes they care about that, and this time they didn't. But okay, so now we're going to graph. I have a 0, 0 point. That's right here. I go ahead and put my 0 there. 0, 0, bam. Some of y'all left that out. And you've already screwed up if you leave that out. The next point is 10 and 5.1. So I go to 10, and I go up to 5.1. That's about right there. 20 and 8.6. I go to 20. I go up to 8.6. That's right about there. 30, 10.4. 30. We're all the way up to 10.4. Just right about there. Are y'all with me here? 40, 11.1, 50, 11.2, 60, 11.5. So 40, 11.1, 50, 11.2, and 60, 11.5. And then I got to connect those lines together. I'm looking for a ruler to make it all nice and neat. You can use the edge of a driver's license or maybe the edge of an extra pencil you brought, if you brought an extra pencil. You guys are pretty lame sometimes. You don't bring pencils. But this is easy enough to do. I'm just going to connect these dots. This is obviously kind of a curve, but it's hard to draw a curved line freehand. If you had a computer doing your graphing, the computer could probably do that for you. And there we go. Beautiful. What a beautiful graph, Mr. Willis. And I did that all in 5 minutes. So, there we go. Now, it says, and by the way, I would have got 3 points for this graph if I did all that correctly. Correct axes, labeled axes, correctly oriented axes, correctly labeled, and with the correct plot of the points. There I get my three points for the graph. And then, if I get the rate right, calculate the rate of the reaction for the time period 0 to 30 minutes. Well, the rate, how fast the reaction's happening, is the rise over the run. So we've run 30 minutes. We've risen to right there, which is 10 point something. It says it in our graph here, 10.4. 30 minutes is 10.4. See? And so we've gone up 10.4 and we've gone across 30. So if I did quick math here, I'll just do it on the side. 10.4 micromoles, you got to put the units, over 30 minutes. And now I could use my calculator, if I had one, to calculate out 10.4 divided by 30. But I know that that's about 1/3, don't I? Because I'm a freaking genius. 10 over 30 is like 1/3. It's a little more than 1/3 because it's 10.4 over 30. But if I do it on my calculator, so that's going to be about, I'm looking for a number about 0.33. Here's calculator. 10.4 over 30 equals 0.3466. So that's about what I was looking for. I'll put 0.35 micromoles per minute. Now if you didn't have your calculator, that's okay, because they gave you anywhere from 0.3 to 0.4 here. Any answer in there would be correct. So that's the rate, and you they actually gave you the point just if you just set up the fraction right. They were pretty lenient here, so you get a point for setting this up right, but you have to have the units. If you left the units out, you get it wrong. Micromoles per minute. So now I should have, for part A, I should have got 4 points there, which I did because I'm great. Explain why a change in the reaction rate was observed after 30 minutes. So in other words, this reaction is going very quickly, very quickly, very quickly, and then it drops off. Why did it drop off? Well, I would say that what happened was it ran out of starch. Remember, if you look up here, it says that we're using starch and we're changing it to maltose in our reaction. There's only so much starch in there. And as the reaction is going by and the starch is changing to maltose, you run out of reactant and you end up with a lot of product. So when I say explain why a change in the reaction rate was observed after 30 minutes, ran out of reactant, starch, so the rate leveled out. There, I get a point for that. And so we got a lot of starch and it's going real fast, and then we're out of starch and it goes real slow. There's other things they would have given you other than ran out of reactant. You could have said that they threw an inhibitor in there, or that the reaction has is one of those feedback inhibition reactions where the product, maltose, goes and blocks the enzyme or shuts it down some way and turns it off. You could have said that too. There's a whole list of things they give you points on as to why this thing curves off. You could have said somebody dumped a bunch of acid in there and the acid denatured the enzyme. Or they raised the temperature significantly after 30 minutes and so the enzyme denatured because it got too hot. You could have said any of that stuff. They're just looking for something decent. So you get a point there if you explain that right. Maybe 2 points. Draw and label another line on the graph to predict the results if the concentration of alpha amylase was doubled. Explain your results. So you're doubling the amount of enzyme. They're doubling the amount of the enzyme. And so what I think is going to happen, if you double the amount of the enzyme, the reaction will occur faster. I'm going to use a green line here so you can see it. And what I would predict, if you double the amount of enzyme, the reaction would go real fast. That means this line will be real steep. Excuse me. So we got more enzyme, we're tearing up the starch faster, so we're going to produce the maltose way faster. So you get a lot more maltose more quickly. But just like this thing, if it ran out of starch to use, then it's going to level off at the same point that this one leveled off. So that's my prediction line. And I want to label that predicted for doubling concentration. And if you don't have a colored pen handy when you're drawing this, you make that a dashed line or something, so that the grader can tell the difference between your predicted line and your actual line. So you want to label this line too. This line right here is the actual experiment. So now we know this is the actual experiment, this is the predicted line. You don't have to write these exact words, just somehow you got to show that this is your prediction. Okay. So, explain your predicted results. So I would say that this, since there's more enzyme, we're breaking down the starch a lot faster, we produce maltose a lot faster, and then it levels out for the same reason that this one did. You have to match what you said earlier. So I'm saying it levels out after 30 minutes because that we ran out of product. Some of you drew something that would look like this. It goes way up here. And that would be legal, and that's fine. That's a fine prediction. But it wouldn't make sense if you said that the amount of starch disappeared. If this original line leveled off because the amount of starch disappeared, then this line wouldn't be able to go up that far, because the amount of starch only was able to produce this much maltose. You wouldn't be able to go way up here with the amount of maltose if the reason this thing leveled off was because the amount of starch disappeared. Now, if you said that this thing leveled off because some inhibitor was thrown in there, or because it got too hot, or because the pH changed, then you could use this line and explain that the inhibitor was added, and that's why this thing levels off too. But this, to me, if it's just that the amount of starch is going down, this line right here is the line that makes sense. So I get a few points if I said that. Explained why this line levels out. Identify 2 environmental factors that can change the rate of enzyme-mediated reaction. Discuss how each of those 2 factors would affect the reaction rate of an enzyme. Well, temperature could affect the rate. If you lower the temperature, the rate's going to be a lot lower. If you raise the temperature, the rate will be a lot faster, because molecules move faster at higher temperatures. So that's an environmental factor. Another one's pH. Every enzyme has an optimal pH, and if the pH is too low, that'll lower the rate of the reaction. And if the pH is too high, it'll lower the rate of the reaction. The pH has to be optimal. Now, we don't know what pH this was operating at, and there may be a more optimal pH. Maybe the changing the pH will make this line even better, even more steep, because it becomes an optimal pH. So the pH can affect the enzyme, because the pH is the amount of hydrogen ions, and hydrogen ions are charged, and they can pull apart the structure of a protein. Those hydrogen ions can. There are other factors. Mixing is one they gave points for. If you stirred it up, it would probably make it a lot steeper if you were stirring. So that is an environmental factor, stirring the mixture. And there's a lot of other ones that you could come up with. There's a whole list of them on the grading rubric, but those make the most sense to me. Okay? So does everybody understand why they got the score that they did? Okay, so what we're going to do now is we're going to have the sub give you the next, another problem that's similar but different, and you do your best to answer it. You can write on the sides, or you can write on underneath, or turn it over on the back to write, but we're going to give you about 15 minutes to do this. It should be about all the time that's left. And then you hand that in, and then the sub is also going to give you a homework sheet so that you can practice these at home tonight too, and that'll be due tomorrow, and that'll count as a quiz grade. So if you do well on the homework sheet, you get a good quiz grade. Okay? Hopefully this made sense to you. Willis out.